Hello, sir.
Yeah, good. Hello, hello.
Sir, good morning. Now we are starting the participant has already joined. Now we are going to start the presentation. Before presentation, the participants, I would like to introduce Dr. Golak Bihari Mahanta. Dr. Mahanta is an accomplished researcher and the academician specializing in robotics, automation, soft robotics, robot grasping and manipulation. Bio-inspired design and digital manufacturing. He holds a PhD in industrial design from NIT Rourkela with a dissertation on robotic grasping and manipulation using analytical and experimental approaches. Currently serving as an assistant professor in the Department of Mechatronics and Automation Engineering at NIT Patna. He has previously held faculty positions as assistant professor at Amrita School of Engineering, Amrita Vishwa Vidyapeetham, Chennai, Karunya Institute of Technology and Sciences, Coimbatore, where he helped to establish the Robotics and Automation Engineering Department. Dr. Mohanta has also industry experience, having worked with the Taikisha Engineering Private Limited, where he contributed to robotic painting system at Toyota Kirloskar Motor Private Limited. Dr. Mahanta has an impressive research portfolio, having published more than 14 SCI Scopus Index Journal, 25 conference papers, and 8 design patents. He has expertise span robotic system optimization, soft material robotics, AI technique in robotics, and digital manufacturing automation. He is proficient in various simulation and design software such as ROS, Gazebo, RoboDK, RoboAnalyzer, MATLAB, CATIA, and SolidWorks. He has been a keynote speaker. His contribution to the innovation include multiple design patents related to precision framing robots, robotic sprayers, and beach cleaning robots. He is an IEEE member and reviewer for reputed journal in robotics automation. With his vast knowledge and experience, I would like to invite Dr. Golak Bihari Mahanta to share his idea on robotic kinematics and motion planning for industrial applications. Over to you, sir.
Yeah, thank you, Dr. Soros. Thank you, Dr. Soros, for this invitation and give me this wonderful opportunity to share my experience with the participants. So I hope they will, at the end of the sessions, they can take some of the experience along, and that they can implement in their teaching as well as in their research. So mostly these sessions will be like kind of very basic like theoretical aspects of these things, and along with like those who are I hope this is actually most of the participant as faculty member. So if they're going to teach the subjects in their classes, what are the tools and techniques they can use, so that it will be more interesting to teach in the classes, and students will be able to get it like more benefit with the help of some simulation tool as well as some programming methods and other stuff. So I'll start with very basic steps. I'll going to start with very basic steps, and I'll try to take through a journey of overall robot kinematics and motion planning. So I'll try to, even though it is a very lengthy topics, and uh, will not able to complete that within a short span of time. So I'll try to like include everything in around 60 to 65 slides, and we'll try to cover like in this particular session, starting from like basic component of I hope maybe those who are completely new to this particular robotics subjects, they will get benefited from this particular session. And those who are already like teaching the subjects and other thing, for them maybe it will be looks like a kind of preliminary talk. But even though it will help you, lot of people those who are trying for some like to join some like NITs or other stuff. So what are the like I'm going to share some of my experiences. I faced like around 8 or 9 rejections before I joined here. So I'll try to share whatever the knowledge, whatever the questions they're going to ask, like some of the basic stuff. So how details you going to study in this particular subject, so that you can like clear the interview and other stuff, as well as you can teach the things in this thing. So uh, I hope my screen is visible. uh, yeah, so what is my screen is visible na, Dr. Saroj?
Yes, sir, visible.
Yeah, so I'll switch up my camera, so I hope there will be no issue.
Yes, yes, please continue, sir.
Yeah, okay. So I'll start with some of the basic simulation. So I'm going to start with some of the basic simulation. So if you see, so this particular software is called RoboDK. Huh? This particular software is called RoboDK. So you can use this particular simulation software to show the practicality of industrial robot. So this will be like consisting of around 700, 800 industrial robots available, and it is freely available. And if you want to get it like paid version of that also, this particular software you can able to do. And what I can show you, like if you see, once you install, if you want like once you open this particular software, this is a like kind of plugin based kind of software. Once you install that in the system, then it looks like this. Then you can open the any of the, if you go to example and other stuff. So I'll try to show why it is necessary. So let me show you some of the example why this basic kinematics as well as this simulation work will be very much necessary. So if you see, so these are some of the like application, industrial application, these are some of the industrial applications. And if I going to run this program, so if you see, so it is doing the like kind of painting operation. It is doing the painting operation. So it will be like with the help of, it is not like a sync painting. So if you see that color part, some kind of camera image kind of thing is going on. So that is like for the these are actually predefined like programs. So this kind of stuff so you can easily show in the classes, so that everyone will be able to understand what the thing is going on, what the thing is going on. And this particular software is like step by step procedure. All the things are available in their YouTube channel of RoboDK. You can easily learn this thing also, like how to program this and other stuffs, how to program this and other stuffs. And this particular software is very much helpful to directly connect to the real robot also. Here if you see some kind of ethernet connections will be there. With the help of that ethernet connection, you can able to connect this particular software to the real robot. So instead of programming like whatever the programming language you have in the particular robot, whatever you purchase, instead of that you can generate your whatever process you want to do in a particular robot, then you can do it. And if you go to this particular website, so if you see, so once you click that link, it will directly take you to this particular website, huh? So here if you see, lot of like whatever the brands you can finish want, whatever industrial robots will be there, it can, everything will be available in this case. And you can easily download it, and you can able to see that thing, huh? You can able to see that how this thing is working and other steps, huh? So we'll start with the robot kinematics part, why it is necessary and why it is important. So I hope all of you know basic kinematics part. So kinematics is nothing but like some kind of motions you need, where regardless of the forces acting on that, we have to study the motions of the any structure. So in robot kinematics also, robot kinematics means it is the study of motions of robotic structure without regard of the forces that cause it. Means like it is very much necessary to understand how these motions will be going to affect the overall conditions of the operations of the robotics things, huh? So before developing any robot, before developing any robots, you have to understood how this robot like motions will be going to happen. So it involves the mostly calculations of positions, velocities and accelerations of each and every, because robot is consisting of some kind of links and joints. it will be consisting of links, joints, and will be having some kind of end effector. So that is the most important thing. So you have to understood how these robots are moving from, like how these links are moving from one position to another position, how they are interconnected, and why it is necessary means like you have to understood the motions of that particular robot, whatever the structures will be there, how it will be going to move. So essential for understanding how each joint and links are contribute to overall motions of that things. Then it will be help you to work with the control framework. So once you know the kinematics of that thing, then you can able to derive the control algorithms out of that. Means like once you know the kinematics, you can develop the dynamics of that, dynamics of robotics, then you can go for the control aspect of that. Then once you know the kinematics of this robotics, you can able to do the path planning, so you can easily accurately like model the like once you know the model of the kinematics, then you can easily do the path planning of the particular step. So it will be coming under the motion planning. Means you have to like avoid, so suppose you have some obstacle and other steps, so how it is going to avoid that obstacle and move from point A to point B without disturbing the intermediate, like without hitting to any objects or other steps, how it is going to move. Huh. And what will be the physical significance of this thing? So mostly like it will be like kind of structural integrity. So respecting the physical constraint of the robot ensure the smooth reliable operations, like then it like energy efficient motion will be required, optimized, like if we have to do the energy optimize kind of steps. Energy optimize in the sense optimizing the kinematics path help the reduce the wear and minimize the energy consumptions. Then precision task will be required, so well defined, so how from one point to another point, or maybe some welding task, painting task, how accuracies can be done. So with the help of this kinematics we can able to perform that. And we will start with the basic robot anatomy. So I hope all of you, lot of you know this particular concept. So I just try to skip as like, little bit go fast in this particular theoretical aspect of these things. So it will be having up like manipulator will be either it can be serial or parallel. It will be having some kind of connecting cable. So if you see like lot of connecting cables will be there for data transfer, or maybe in some kind of power plugs and some data transfer kind of thing. And if you see that particular yellow button kind of link, so this is mostly for pneumatic pipes, because end effector what will be going to fit in this, because whenever we are going to purchase a robot it comes like this. So it is a kind of bare structure along with the stitch pendant. Here you can see stitch pendant, and the controller box will be here like this. And you will be having lot of cables, so maybe it will be sensing cable or pneumatics cable, or maybe to control the actuator some kind of power kind of cable needed, huh? And it will be like controller hardware will be that this particular box if you see here. Then teach pendant for programming this one. Then end effector tool will be going to fit at this particular end. So if it is a general purpose machine, you can able to add a gripper here, you can able to add a painting on here. But if you add a gripper, then you have to, if it is a like pneumatic gripper, you have to supply through the pneumatic power. But if it is a electrical gripper, then you have to use electrical power to do that. And if you want to do some kind of welding in this particular robot, then other setup also you have to add along with this particular base controller. You have to add the welding gun, then along with that some kind of feeder you have to add, then some kind of transformer you have to add, like because it needed high voltage kind of stuff. Then for painting operation you have to use paint gun at the end here. Then you have to use some kind of other in painting shop they used to call that like kangaroo boxes. Means like it will be some kind of thinner will be there in one side, and another side one paint will be there. Then you have to mix it so that it can easily like smooth. Then some kind of pump will be there to pump that liquid so that it can able to spray properly, yeah. So these are, then along with that some kind of softwares will be there. So for each and every robot, mostly those industrial robots, each and every robot having their own softwares for that. So you have to understood the basic syntax of this particular thing, and these are mostly called VL programming language. So mostly it will be written as move A, move B, like this kind of stuff. In backend, the softwares will be written in either C++ or Java, but it is a kind of user friendly like basic programming language similar to your CNC machines and other stuffs. Huh? So next thing, mostly these particular robots and everything, na, so it will be like coming under this particular ISO. So ISO 9946, and in ISO 99 under 9946, different ISO are there for different aspects. So one is like 8373 is there. All these related industrial robot definitions, everything is all this vocabulary related to this robotics are put in this ISO 8373. Then other stuff. Huh? Just keep this part. So next most important thing, when you going to purchase a industrial robot, this will be coming with a this data set, and this is the most important thing to understand. So you have to understood each and every component of this particular data set, then only you can able to like understood what the things is happening in the industrial robot scenario. Huh? So first thing is called the payload. If you see, it is mentioned that this for this particular model, this model company is Stabuli. So fast in this particular case, the payload is given as around 33 kg, and it will be like 66.1 lab, or and it will be like some conditions will be given, but different model, different payload is provided in this particular case, and nominal payload is like 20 kg and maximum is 30 kg. Huh? So what is the meaning of this payload? So the payload is nothing but the maximum weight of a robot that can lift in all possible configuration within the specified workspace. So what is the meaning of that? So if you see, this is a industrial robot, and it will be like it is holding this particular object in different configurations. Huh? So whatever the like all possible ways it can hold, means like it is not like that if it is like 30 kg here, then if you go to this particular configuration, it cannot able to hold that 30 kg. So that's why what all possible configurations will be there in the specified workspace. Then it is like because if you see, you are not able to hold. If you just imagine, if you want to hold like lift a 5 kg object. So like in a in the like if you hold that and put that in your head, and in a single hand if you want to lift, so 5 kg object you cannot hold it for a very long time. After some time, because we are like human beings, so we are not able to hold that for like very long time. So we cannot say that my payload will be kind of 5 kg kind of scenario. So for each and every particular configuration, how these things will be able to like maximum load will be there. That is coming under the payload of a robot. Then next thing will be, another thing will be called supplementary load. So that also it will be like mentioned in some cases. It is in this particular case it is not mentioned, but this particular supplementary load is also very much necessary. It is also defined in the particular data set. Means like suppose you're going to add some of the extra load to that. I mean that how you going to like where are you going to add that, and how much load, maximum load it can hold. So in this case, if you see here, one extra mount is attached in this case. So this particular position, particular link is also will be provided while you're going to purchase this one. So apart from this particular point, you cannot add any other point, any of these things. So if you're going to add, then what will happen? You cannot get the full potential of the robot. Maybe some issue will be going to happen. So next thing will be a number of access will be there. So it is like normally the degree of freedom of a typical industrial robot, how many accesses are there. So in this case, if you see, 4 access are there, here 6 access are there, here 7 access are there. So in this case, so if you see, so what is the meaning of this particular access part? Let me go to this station. So if you see, this is the number of access. So here it will be having 6 access. This is my fast access. If you see, this is my fast access. Though this is like represent RGB, means R is your x axis, your green will be your y axis, and blue color is your z axis. So if you see here, the fast joint is at the base, and it is rotating with respect to z axis. This is rotating with respect to z axis. So this is the fast axis or fast joint, you can tell, because each and every, because this is a like articulated robot arm, it will be having all joints are rotary joints. So rotary joints is having 1 degree of freedom. Rotary joints will be having 1 degree of freedom, because degree of freedom, if you imagine any object in space, then it will be maximum, without constant it will be maximum having 6 degree of freedom, means three directional like XYZ, three linear motions and three rotational motions will be there. For rotary joint, what happens? Remaining five joints are constant. So rotary joints only single degree of freedom will be there. So this is nothing but my single like first axis. This is my second axis. So it is rotating with respect to either it will be with respect to some y axis, then this is rotating with respect to x axis, this is rotating with respect to again your x or y axis, then fourth joint, fifth joint will be there, then sixth joint. So each joints will be representing one degree of freedom, rotary joint, so that each and every degree of freedom is like this is a 6 degree of freedom robot I can say, because six joint independently rotating like with each means with respect to irrespective of the other stuff, independently it is moving. So if I going to rotate this joint, so other joints are not moving because we are in the Cartesian frame and other frame so that's the degree of freedom part. Then next thing we're going to thing is the mounting flange. So this is also one of the most important things. So this is going to follow that ISO 9409 part. So whatever the robot will going to purchase, if you see this particular end effector part, so these things they have to follow this ISO standard, so that because see the robot manufacturer they don't usually go and develop this end effector. For end effector different other company will be there. So those who are having the robotics in their lab, they can experience this one. So they have to follow that, so that like whatever the end effector that you're going to put, it can going to attach to this particular flange so that particular steps everyone has to follow this and ISO 9409 and going to develop this one then next important thing is called repeatability. Pose repeatability. So pose repeatability measures the variations of the in the actual position and orientations achieved by a robot when instructed to repeatedly return to that particular position. Just imagine I want to take my robot to a position called XYZ where I gave the target as 100, 200 and 300. So it has to reach to that point. So what happens initially when you take for the fast iteration, it reaches maybe 99.9 mm and 200 instead of 200 it reaches what? Instead of 200 it reached 201, and the next time it reached 300. So in second iteration it reached this point, third iteration it reached this point. So what happens, it is continuously going to the nearby position nearby position. So what happens, whatever the positions you reach at the end effector position you reach, if you take a small radius of that particular thing, so it will be going to develop a spherical kind of thing, and whatever the minimum radius of that particular sphere means like the end effector position you will get, suppose here he first case you get here, second case here, all these things. So if you consider this particular points, what will happen, it will be going to develop a sphere. So you have to measure the minimum radius of that, and that radius will be nothing but your pose repeatability. So how accurately it can going to develop reach that particular thing so if you see each and every robot will be coming under some kind of repeatability thing will be provided to you. So like for Fanuc, this particular repeatability is plus minus 0.05 then this accuracy means this particular value, lower the value it will be like more accurate compared to higher the value. This is like pose repeatability. This is one of the other important aspects of this particular part. The next thing will be called mounting position. This is also defined in this thing. So how you going to mount that particular robot? You cannot mount like haphazardly. So whether you can able to mount in vertical position or horizontal position or some other slotted devices or maybe some kind of other application. This thing we also mention in the part. The next thing is called working envelope. So different how working envelope is nothing but it is the space which a robot can operate it is a space where the robot can operate. So different working envelopes are there: cylindrical, Cartesian, spherical, and articulated. So if you see, these are some of the work envelope visualization. So if you see, this robot is called a SCARA robot. SCARA robot will be having base is rotary, then your prismatic joint, then your again rotary joints will be there at the end. This is a rotary joint, this is a rotary joint, then this is will be like prismatic joint, and this will be your end will be again rotary joints. So if you see here, some constant will be there. So here it is a kind of cylindrical work envelope will be developing, and at the back some kind of, due to the physical limitation of this robot, you are not able to reach the back side of this one, huh? So because see, physical restriction is the most important thing, because joint, you cannot just imagine your hand, you cannot make, so that hand is also kind of rotary joint, so you cannot take it to the backside of this. So if you take it backside means the maximum go up to maybe some like even if you see, if you cannot close it properly, huh? It cannot close it properly. Maybe it can navigate from 10 degree to 180 degree. If you take it to like backside, then it will going to break your hand. So that restriction is very very means like physical joints, you cannot do this thing. So why this, if you see, I'll going to show this particular simulation again. This is a MATLAB simulation I wrote, basic MATLAB simulation. So this is for a 2 degree of freedom robot. So let me, I hope the screen is visible. So if you see, this is a 2 degree of freedom robot, and this red dot is showing that joints, and the green dot is also showing the joints, and this blue is L1, this is L2. So what is happening, I wrote this for a particular theta 1 and theta 2, and if you see like for each theta 1 value, suppose you take theta 1 value 20 degree, then this theta 2 you have to rotate it for like 0 to 360 degree. So that it is happening, huh? That is happening. So maximum possible way how much it can able to reach the robot, huh? So this particular space is called physical space, and this particular space is called configurational space. This is a kind of theoretical space, maximum theoretical space the particular 2 degree of robotic arm can means like reach. So in this case, if you see, this is a rotary agent is continuously rotating, so without any restriction. But in real life, what happens, this particular rotary joint, it cannot rotate continuously, because some constant will be there, huh? Some constant will be there. That's why you are not able to rotate it to completely like 360 degree. Theoretically you can able to show it. So if you see, this is a 2 degree of freedom robot. If I say what is the configuration space means, for this like all value of theta 1 and theta 2, what will be the space it will be generate, the end effector will be going to generate what is the maximum work envelope or work space it is going generating, huh? So that is configuration space. So for this particular condition, it is become a torus. For different applications, suppose it is a like other joint, it may be like other kind of space you will going to get, huh? Other type of space you going to get. So it is means like this particular circle, if you see, means it is going to reach each and every point in this particular torus, huh? It particular torus. So that's the thing, huh? So so I hope I'm going to stop it. So in this case, if you see, it will be going to generate this kind of for this particular robot. So how will going to do that? While you code that in MATLAB, na, you have to take the physical parameters of each these things, develop the forward kinematics equation, develop the forward kinematics equation, give the loop, and you can able to plot that tracing part, so that you can easily able to get that. Huh? You can easily able to get that, and yeah. So next thing will be what is the key differences between the one is called work envelope, one is called work volume, because always it will be like kind of confusing thing, huh? So lot of time in interview they used to ask what is the difference between this work envelope and work volume. So work envelope is nothing but a kind of a two-dimensional space, means maximum it can able to reach, like there is no restriction at all. So geometric shape defining the boundaries, which means like it will going to define the boundaries of these things, typically visualized in two-dimensional space. So it all the reachability boundaries can be denoted by this work envelope. But work volume is nothing but the three-dimensional or operational space within the boundaries. So if we see in this case, if we going to develop a like overall work envelope, I can say that like kind of circle kind of stuff, huh? Circle kind of stuff. But if the work volume will be exactly like this, work volume will be exactly like this, huh? This is operational capacity. So next another thing is you have to understood you have all these particular stuffs are like rated by this ISO 20635, that is for your ingress protection. Means if you see ingress protection is like IP65, while you going to means like buy anything, means like this is a kind of waterproofing condition kind of stuffs. So how it will be going to do that, huh? So in this particular case they are going to follow the IP65, means for totally protected against the dust, because a lot of dust and other stuffs will be there, huh? And some kind of protected against low pressure water jet from the direction with limited ingress, huh? So it means like you cannot put that in underground and try to like that if it is a like different kind of actuators, then they can go for the underwater application also, but for that they have to follow different ingress protection kind of thing. This IP65 they have to follow, and in that case whatever the like protects different kind of depend upon the motors and other stuff, they can go for different IP similar to your smartwatch and other thing, na? Like you have to waterproof IP6, IP7, IP8 they used to tell. So this is like for both, but in this case you have to use both, like for solids as well as for water also you have to do. Next thing will be your axis data. So axis data is nothing but if you see each joints will be both joints will be going for positive as well as negative part, huh? Like if it is moving clockwise you have to define positive, it is anti-clockwise you have to define negative. So both thing you have to do specific, like in which side you like plus and minus everything you have to do. And you have to calibrate whenever the robot will be going to come, you have to calibrate each and every joints, huh? Like this is my joint 1, this is my joint 2, then you have to calibrate these things before make it run, so that you can easily there will be no issue will be going to come. Next thing, this configuration space we already discussed, you already visualize that thing. So configuration space is nothing but like where is that particular thing, means like where is your robot. So that thing you have to know in very details, huh? Like just imagine a door, like if you're going to like open that door, so what are the variables you need for that to define the position of that door. Maybe it is 0 degree means it will be closed, 90 degree means it may be open. So in that case you need a single variable, that is your angle. So this configuration space is nothing but my angle of the hinge, huh? Angle at about its hinge. Then just imagine a point. So how are we going to define a point? So to define a point we need x and y only. So in x axis how much, this one, y axis. But if it is a object, imagine if it is a object, then it will be having xy, as well as if it is a two-dimensional place you need another theta value, means how it is oriented, huh? Then if it is in a six-dimensional space, means you need xyz as well as theta 1, theta 2 and theta 3, position, three orientation you need. Similarly for this planar robot, either you can define in the form of joint angle theta 1 and theta 2, huh? And same thing for this particular robot, what is the configuration space. So you already see that this configuration space for these two joints are s1 and s2. So this will be kind of torus, it is forming a torus. For theta 1 it will be like one configuration space s1, and theta 2 another will be s2. So both will be going to make a torus, huh? Then what are the components for this to develop the configuration space? Is degree of freedom is the first thing. So degree of freedom is nothing but the number of independent parameters required to uniquely define the configuration of the system. And this is another thing interviewer usually ask in very like details, means like details in the sense they will go into the depth of this particular degree of freedom part, and they'll try to extract as much as thing possible, like try to make you, means like if they're going to ask you like means like as I show you, know, like each and every I'll going to show you this particular scenario, huh? So if you see these are the types of joint actually generally used in any of the scenarios. So one is revolute joint, so that is denoted by R. Then one is prismatic joint is P. Then your helical joint is your H. Or this is also called screw joints, means like it is a screw will be there, it will be screw will be there. Then cylindrical joints, this is only like there is no screw at all, so helical joints. Then universal joints and spherical joints. So revolute joint degree of freedom is one, because it is only going to rotate with respect to any of the axis where you're going to put this joint, restrict between these two links. then prismatic joints will be there, then helical joints will be there. So this is the most commonly asked questions, like this helical joints degree of freedom will be 1. So this is revolute joint, degree of freedom will be 1, means independently in one axis it will be going to rotate. It cannot rotate in any other axis, means like whatever the axis is. Suppose you put that joint in vertically, suppose if you see, if you're going to put that in vertically, means if you're going to put that in vertically, it will be going to means like what is the meaning of this revolute joint. So I hope if you able to see this particular scenario. So this is a rotary joint, this is a rotary joint. So if you see here, it is put that in with respect to z axis. So it is with respect to z axis only, it is rotating, it is not rotating with some other axis. So if you see, this particular joint is with respect to red color, second axis. Second axis is rotating with respect to x axis. Understood na? So it cannot rotate anywhere, it cannot rotate anywhere else, so that's the most important thing. So you have to understood this very very clearly. But another thing I'll going to show you, that one, the this particular scenario. So let me go to this website and going to so see how we're going to do that. Suppose I want to with the help of 4 axis I want to do, so if you see, these are different robots are there. So I going to add one, maybe this is a Scala robot or something. I just simply download it, or directly I can make it open it. So open in robotic, so it will be going to open. So if I going to see, this is my robot. So in this particular case, if you see, so let me yeah. So in this case, I be going to click, see, this is my robot, this is my robot. So it will be having 4 axes. So if you see, this is my first axis, this is my second axis theta. But if you see, third one will be having what? If you see, it is a it is a which kind of joint? This is a, either it will be a like cylindrical joints, or it may be a spherical joint. So mostly it will be a spherical joints, but because here some kind of screw will be there. So what happens in spherical joints? So it is a degree of freedom 1, because independent motions are not available, because thread will be having minimum pitch. So in this case, what happens, if you rotate, suppose like one rotation, then it can travel up to 1 centimeter. So that will be the minimum pitch will be there. So that independent rotations are not there. That's why this particular thing is called degree of freedom 1. So spherical joints, everyone remember, this will be like degree of freedom will be 1, and you can easily show that. Then again, fourth one is the last one. This is nothing but the end effector part. This is also again rotary or R kind of joint, so that's why this is very very important, degree of freedom part. So next thing will be, yeah, so here just go through that. I already defined the links and joints and the other stuff, so you can go through that. Then next thing is how to find out the degree of freedom. So in robotics, we generally going to use this called Grubler's formula to find the degree of freedom. So it is denoted by m into n minus 1 minus summation of ci or fi, whatever you want to call it. So m is nothing but the depend upon the which plane you are doing. So either it is a two-dimensional plane or three-dimensional plane, and depend upon the number of, if it is a two-dimensional plane, we need minimum 3 parameters to define that thing. So here this m will be becomes what, 3. So if it is a two-dimensional plane, and n is the number of links, n is the number of links, and j is nothing but the number of joints, j is the number. Here actually another stuffs will be going to come. So in this case, a ci will be like this constant impose. If you put the constant impose, it will be this particular j part will be also going to come. So expanded formula will be this one. So number of n minus 1 minus j, summation of f of I, means independent degree of, means like this is the summation of in number of degree of freedom of each and every joints. Suppose we're going to calculate for this particular one. So if you see, this is a 2 degree of freedom robot. So if you see, this green one is the link one, this is another link one, it is joined by a rotary joint. This particular one is nothing but the rotary joint. Then between this link 2 and link 3, this is joint 2. So joint 2, this is also a rotary joint. So here how many links are there? 1 2 3. So n is 3, then joints is 2. Joint is 2 means here if you see, this is one rotary joint, this is another rotary joint. So joints are 2, and these are two revolute joints, mean each joint will be having 1 degree of freedom. So 1 and 1. So if you add that summation of 1 plus 1, you will get summation of f equal to 2. So your degree of freedom will be nothing but 2. So this is a 2 degree of freedom. So if you see the two joints are there, so you can easily see that this is a 2 degree of freedom robot. Huh? Then next thing, this is another like theory of machines questions like 4 bar link mechanism. So if you see here in this case also, here how many links are there? The base is the one link, second link, third link, and fourth link. And here how many joints are there? One, two, three, four joints are there, and all joints are revolute joints. So 1 degree of freedom each. So this is summation of this one will be 1 plus 1 plus 2, 3 plus 1, 4. So if you put that in the formula, you will get the degree of freedom is equal to 1. So next thing will be this particular slide. So this is a parallel robot kind of thing. This is a parallel robot. Huh? This is a parallel robot. So in this case, if you see, it is written as S. S is nothing but spherical joint. So spherical joints degree of freedom will be 3. Spherical joint degree of freedom will be 3, and P is nothing but prismatic joint. So degree of freedom will be 1. So if you see here, it is written spherical joints is 3, and this here if you see at the base one joint will be there, and at the top part one joint will be there. So it is written as f3 equal to 3 and f1 equal to 1. Prismatic joint f1 equal to 3. So how to calculate the number of links? So number of links, this part first part is the number one. This is base is another one. Base is another one. If you see here, two links are there. It's connected by one prismatic joint. 6 into 12, 6 into 2 means like each joint will be having 2. So it will be having 1, 2, 3, 4, 5, 6 links. So 2 means 2 into 2 is 14. So n equal to 14. So n equal to 14. Base part is 14. So n equal to 14. Then joints, number of joints here 6 at the base, 6 at the top. So 6, 6 plus 12, and here is between two links, this link and this link, one prismatic joint. So 6. So 18 joints are there. 18 joints are there. So now if you're going to add each link summation of fi, so one joint is having how many spherical joints? 12 spherical joints. So 12 into 3, 6 means 36 plus 6 prismatic joints. So 36 plus 6 means 42. If you put that, you will get that toward platform degree of freedom you are getting as 12. Huh? So these are the very preliminary stuffs related to robotics. So I hope you have some of the like clear understanding in this case. Next we're going to discuss about the kinematics part. So in robot kinematics, mostly two kinds of kinematics are there. One is called forward kinematics, second is called inverse kinematics. Forward kinematics is to find the position of the robot, then inverse kinematics is to find the position of the joint angles, position of the joint angle. So in the forward kinematics equations, your x, y, and z thing you have to find out your known condition will be length and angles will be provided, but in this is the other way around. So how to find this particular thing? So you have to first know about all these parameters, then you have to find out dh parameter representations, because then next will be find the kinematics equation. Then you can easily, once you multiply each and everything like from 0 to 1, 1 to 2, 2 to 3, like that you can find out. Then you can able to find the final end effector position and as well as orientations. So it will be coming as a 4 by 4 matrix. And the out of 4 by 4 matrix, that 3 by 3 matrix will be the represent the orientation, and the position will be px, py, and pz. So how to do that? I'm going to share this particular slides with you. So I developed one flow chart for this one. So once you understood this particular concept, you can easily means like develop the dh parameter. So it will be very much helpful to teach in the class. So this is a continuously a flow diagram will be there. So so first thing, in dh parameter algorithms, what you have to do, like, because this is mostly used for industrial robot and it is developed in around 1956 or something, but later on some advanced methods are already there, but still we are like screwge methods and some like other methods are we are generally now exponential equations method we generally use, but till now mostly for teaching purpose we are following this dh parameter notation and other steps. And this is also there in the syllabus of engineering services examinations. So the dh parameter part. So what happens, and always remember, in dh parameter part they're going to ask you a very detailed questions. So first thing they're going to ask you so what are the assumptions you're going to take to develop this algorithm. So first thing you have to mention that This is only for the valid for the binary joint. So if it is like ternary joints or quaternary joints or some other joints will be there, you are not able to apply this. So generally these methods are, we are not going to use in kind of parallel robots. If you're going to use it, means you have to again like convert that ternary joint to binary joint, then you can able to calculate it, huh? So first thing in this case, that is the most important thing. And we have to use the right hand thumb rule, means we don't use any others, only we going to represent according to Dynamite and Hartenberg, we only use x and z parameters. So automatically as right hand thumb rule will be applicable, your direction of y will be very much like automatically it will be like understood, huh? So then they used to ask the demerits of these things also. Demerits means what happens sometimes you can maybe while you do assign the points, nah? Sometimes you maybe miss the like some points, like in any joints the some kind of points will be not available, then some kind of issue will be going to come, like singularity and other stuffs will be going to come. So first thing will be what you're going to do, like you have to first notate all these whatever the joints you have, you have to first assign the z axis to that particular part. Whatever the joints, you have to add the z axis to that. All the joints in these parameters has to be denoted by z axis. So if you see, either two kind of joint will be there, because only we're going to use 1 degree of freedom joints in this case. We cannot go for like higher degree of freedom joints in the case of dh parameter. So either it may be prismatic joint or it may be revolute joint. So in this case you have to denote in this way. So if you see along the ith axis joint, zi towards the direction of zi plus 1, means like what is the meaning of that? Suppose you will having this example, huh? So here what you going to do, this particular theta 1 you have to access as zi here, and this will be your z2, z1 will be here, z2 will be there, this will be z3, means like you cannot like start and put somewhere else. So how this will be like, how this side will be there, in that way you have to go towards zi plus 1, huh? It is preferably zi towards the direction of zi plus 1, means like next directions. Then prismatic joint, next thing will be go for the assign of the origin. So once you assign this particular axis, then you have to assign the origin of that thing. So in origin also three conditions will be coming. One will be zi and zi plus 1 will be intersecting. If two joints are intersecting, then always you have to put your reference point at the intersection point. And in the previous joint, suppose it is zi and zi plus 1, if it is intersecting at zi, then you have to put the number as, suppose this is your z0 and this is your z1. So what will happen, this numbering will be at this particular point and it should be 1, because between 0 and 1, which is the previous one, the previous one is the I1. So always in I axis you have to denote this one. And a lot of people make mistake here. So what happens, so they will take means like this point, like even this is not joining at the point center. Just imagine two are parallel, imagine just two axes are parallel, like at one it will be top. So what is the meaning of this? So one second, so let me draw it little bit. So what happened, a lot of people make mistake in assigning this axis. Just imagine this is one joint, huh? Then another joint will be here, another joint will be here. So as I told, so you have to assign the z axis first. So this is my first z axis, this is another z axis. So this will be my suppose z0 and this is my z1. So what happens while they assigning the number of this to the point, so they what they did, they just extend this one like this, and here they are try to extend, and this point they try to make this as 0. If you going to make that this like this, means you are totally wrong, because if you see this point is not at this particular joint. So you have to try to remove this mistake. Lot of people they mistake, so you have to understood that this particular reference point should be at a joint. So instead of doing that, what you will do, instead of doing that, you can do like this, you just extend this position like this, extend this position like here. Here this is my thing, so this is my what, this is my reference point. So this is my, instead of this point, this is, so if we take this reference point here, then you can easily it is at the what one joints, it is at one joint, huh? This is a like same basic mistake they, a lot of people they used to do while assigning the access. Then similarly, if you see in this case, in second scenario, if you see, huh? So just go through my mouse. So in this case, if you see, this is my Z1, I is going like this, Z I plus 1 is like this. then what is happening, it is at the which joint, it is at the zi plus 1 joint. But even though if it is at zi plus 1 joint, what you have to do, you have to locate at oi will be here. Oi means whatever the zi value. Suppose this is your z0, this is your z1, then this particular point will be your z, means like o point, means like 0 point. This part will be 0 point. Don't mean like it is not, it is in the one line, z1 line, but don't write it at one. Always it will be between the previous and the new one. If it is z1 and z2 means this point will be becomes 1, because this is z2 and z3 means this point will becomes 2 numbering while you do the numbering. Similarly you can go for the other one. So if it is parallel, then it is what, you have to draw a common normal and you have to put the point in that common normal. Then if it is both are collinear, then you can anywhere you can put, anywhere you can put, but try to put that in the any of the actuators or the joints, actuators of the joints. So once this thing will be completed, you have to assign the x-axis part, you have to assign the x-axis part. So one will be your when both are what, both are like kind of intersecting with each other. If it is intersecting with each other, then you have to find out the means like plane created by the intersection, and it will be perpendicular to that line. So if you see this axis and this axis are intersecting, so it is creating a face here. So this you have to draw a line that is perpendicular to the face. So the direction of x will be in this direction, in this direction. Similarly, if it is a parallel, then you have to go for the, you have to draw a perpendicular direction to this particular axis, and draw the axis will be towards the axis of this one. Then in collinear you can put in any direction. Any direction you can put, that depends upon you. Once all these condition will be completed, then you have to fill this particular thing. And in this case, these four parameters are there. One is link length, twist angle, joint offset, and joint angle, and some sequence you have to follow. So past will be twist angle will be there. So the twist angle is nothing but, if you see, I'm going to show you another confusion lot of people are going to make this related to twist angle. So what is the meaning of this twist angle? So this is a valid point, means like it is a initial what do you call, one second. So yeah, so this is the twist angle part. So twist angle is nothing but this is one joint. This joint, this particular joint is arranged vertically, this is arranged horizontally. So whenever the means like what is the angle between these two things, what is the angle between these two things? So if you see, imagine if the angle between these two things is 90 degree, 90 degree, but you have to follow the right hand thumb rule. So you have to check that, means like if I going to rotate this particular axis, how much angle it will going to make it parallel to this one. So that much angle, and it is a imaginary kind of thing. In you don't think that, don't think that as like different stuff. So means like it is a, whenever you going to purchase, means like fabricate or create this one, this thing you have to decide by yourself. So how the joints are angled. So in this case, joint 1 and joint 2 are twist, means like angle are 90 degree. This is my joint 2, this is my joint 2, and joint 3. So here twist angle will be how much, both are parallel to each other, so twist angle will be 0. It is not like that it is rotating. So if you see, even if I going to bring this to here, this is my joint angle 2, joint angle 2. So both are, if you see, this is my joint angle 2, joint angle 2. So both are, if you see, these joint and these joints are parallel to each other, means your twist angle will be 0. Twist angle will be 0. So this is given by the company. This is given by the company, that you have to fill, and fill the sequential part. Once you fill this, you will get this equations. You will get this particular matrices. You have to remember this matrices. So you instead of developing each and every matrices, you can develop, this matrices from this table. From each and every table, you can, like, from 0 to 1. So you can get a one transformation. You will get one transformation like this. In this case, if you see, once you this is a basic like RRR configuration part. So here once I did everything, like this is my, initially I gave z0 like here z0. Then for this particular, this is my z0 means the base point where the robot will be going to add come joint, means like robot you have to put in some place so you have to put that robot in some place. So that is z0. And for this particular blue color part, I gave this as z1. So it is, you can extend up to this point. For this second joint, this z2. For third joint, Z3, and fourth point is nothing but there is no joint at all, but I can show that this for end effector I just draw that Z for an X4. So now once this assignment of Z is completed, you have to assign for the 0 point. So if you see between Z0 and Z1, if it is collinear, so I can write the point at here 0 point here. Then I can look for Z1 and Z2, it is intersecting, so the 1 point is here. Then Z2 and Z3 both are parallel, so if I draw a line there, so point 2 is starting point here, 2 point is here. Between 3 and 4, starting point is 4, and fourth one is our point. So this point is completed. Then you will draw for the x-axis. This is my Z0 part, so I can write one axis here. Between 1 and 2, this is making an plane, this one. So here x1 will be like this. Between x2 and x3, directly you can draw x2 here, then x3 here, x4 here. Once you assign all these things, then all this table you have to fill up. Once you fill this particular table, if each and every value you have to put in this particular slide. So 0 to 1 you will get one matrix, 1 to 2 another matrix, 2 to 3, 4 to 3 to 4. Then if you multiply, they represent the orientation of that particular position, and this last like px, py, pz represent the position of that point. So this is nothing but the forward kinematics value. So using this particular forward kinematics value, you can able to develop the workspace also. You can able to do the workspace also. Then next thing called inverse kinematics part. The next thing will be your inverse kinematics part. So in this particular case, we have to find out the joint angle provided your x value, y value, z value as well as link length will be given. So you can able to find that. And different why necessary this path planning, peak place, and other stuffs will be there. Then how to find different solutions will be there. So one is analytical approach. So in analytical approach, how will do that? So you can solve these two equations. Here two unknown, this is known, this is L1, L2 known, theta 1 and theta 2 unknown. So once you solve this one, you can get two value. So one will be theta, two will be get cos inverse this one. So but in this case, if you see, we'll go get two value of each value, theta 1 and theta 2. If you see, if I going to see like cos 90 degree, cos minus 90 degree, 45 degree minus 45 degree, we are getting two corresponding value. Means if you see, this is my bottom kind condition. So in this case, if I draw like this, another conditions I will get. So that's why two value will get, means like multiple value will get in inverse kinematics. That's why inverse kinematics part is very complex. So for particular applications, if you want to develop some robot or something, so lot of paper or research article you can get, lot of people are there focusing on different approaches to solve this one. These are the standard kinematics part. Then some of the pros and cons I mentioned. Exact closed form solutions, very fast computation you can do, suitable for real time control. Then not applicable for complex because it is very difficult to develop for complex geometries. It is very difficult to develop. And then next is iterative methods, and like iterative method or numerical method. You have to use some kind of form called Jacobian based approach. So this also we're going to discuss what is this meaning of this one. And then Jacobian method or Newton-Raphson method. Any mathematical approaches like iterative numerical method you can use here. Numerical mathematics you use to study, like that approach you can able to do it. Then optimization based method, in this case what happens, you have to develop the for you already know the forward kinematics value, then whatever the desired value you are getting, so you have to minimize that with respect to some optimization method. So you have to develop a optimization function, then you can minimize that one using any of the method, any of the method. Then some kind of heuristic or AI based approach will be there. Genetic algorithm, PSO, lot of paper. If you see, like lot of paper you will get based on this AI methods and the other stuff. So you can explore that part. Then these are some of the comparison for that. Then in traditional methods, like in theoretical aspect, in classroom while you're going to teach, how will do that. So to inverse kinematics part, again the same thing you have to follow to find out the forward kinematics. Once you complete that part, you will get this px, like px, py, pz. So based on this particular data, this is nothing but my x, y, and z position. From this particular position of forward kinematic solutions, I can compare this value and I can get the theta 1, theta 2, and theta 2 value. D in this case it is D3 value. It is D3 value because this is theta 1, theta 2, and this value will be a D3. your R and prismatic configurations will be there. Huh? So in this case, you can able to find inverse kinematics part. So next important thing is called your robot Jacobian. So what happens actually? So each and every joints will be having their own like theta one, theta two, theta three value, theta four value. Huh? But in end effector, that is my end effector position will be x, y, and z. So what happens? Though joints, whatever joints will be having, each joint will be having their own velocity, and due to that particular velocity your end effector will be going to go from one position to another position. So in that case, your suppose imagine the joint will be rotating in a suppose radian per second or degree per second, your velocity will be there, but end effector will be maybe moving in x direction at a meter per second or some like centimeter per second, whatever the thing will be there. So one thing is called that's why it is very difficult to do that. So what you have to do, you have to map that velocity like joint velocity to the end effector velocity, to that end effector velocity. So that thing will be done by the Jacobian matrices. So how will do that? So x dot is the end effector velocity, q dot is the joint velocity, and the Jacobian term will be coming here. So to mapping the mostly it is used to map the or relates the joint velocity to the end effector velocity. Similarly, it can do the mapping for force and torque. Because see, if it is a rotary joints, the torque part will be coming. If it is a prismatic joint, the force part will be coming. So it will be going to map that things. Then it will be used for inverse kinematics also. Jacobian already saw you. Then optimization and control, it will be very well helpful. So how to do that? How to do that? So x and y, you know, this one is a general geometry. So in this case, your x will be xy and q will be theta 1 and theta 2. Then you have to take the partial derivative because it is not like independent variables. Both are dependent variables. So you have to do the partial derivative once you do with respect to theta 1, once you do it with respect to theta 2. Means like dx by d theta 1 and dx by d theta 2. Similarly, dy by d theta 1, dy by d theta 2. So once you write these things, you will get this particular value. You will get this particular value. So this particular thing is called Jacobian. This particular thing is called Jacobian. So this thing is called Jacobian. So in this case, if you see, this is nothing but this is a matrices. So if you going to see how, if you in this particular case I want to find out the theta dot. In this particular case I want to find the theta dot. So what will be going to happen? So let's see. Uh, I just want to find out the theta dot in this particular case. So in this case, I want to find out. So this particular relation is given. So I can easily find out q dot is nothing but what, j inverse of x dot. So I can if I know the x dot velocity and effector velocity and the theta like the j in one inverse, if I going to find out, then I can easily find out the joint velocity. Joint velocity is nothing but my theta 1 dot and theta 2 dot. This is nothing but my theta 1 dot and theta 2 dot. So if you see, this joint inverse is nothing but this j inverse is nothing but what, how to find a inverse of a matrix. This is nothing but your adjoint a, this is adjoint of j divided by your determinant of j. This is nothing but your adjoint j by determinant of j. So if you see now, whenever this determinant of j will be going to become 0, this determinant of j tends to 0. If this will be 0, then what will happen? This your j inverse value will be going to becomes infinity. This j inverse will be going to becomes infinity. If this value will be going to infinity, your velocity will be going to infinite. Theta 1, theta 2 becomes infinite. But that is not possible at all, because each and every robot will be having certain velocity. So it can start from some zero velocity, it will go up to maximum velocity. What is the limit of that particular joint? It cannot reach up to infinite. So if this is the condition will be going to happen, what will happen? Your robot will be actually will be going to face lot of like jerk, and it will be not possible at all. So what happens? We have to find out the condition where this determinant of j will be becomes 0. So some condition we have to find out. So where this determinant becomes 0, whatever the position or whatever the condition this determinant becomes 0, that condition is called the singular conditions. And this is also another important topic. Everyone going to ask you this particular part. A singularity is configuration where the robot loses one or more degree of freedom in task space. Mathematically, it occurs when the Jacobian matrix become rank deficient. Rank deficient means your rank j will be less than or equal to minimum n of n in Cartesian direction. Or mathematically, if you going to write, your determinant of j will be becomes 0. So if this will be becomes zero, the joint velocity cannot be means like uniquely computed. It will be kind of infinite kind of stuff. Huh? It is very difficult to particular value. So if this particular condition I already mentioned, so small Cartesian motions require very large joint velocity. Huh? Then if you do that, what happens, like if this particular velocity, and if velocity will be becomes infinite, then your energy also becomes infinite. So loss of motion, or then what happens, high energy consumption will be required. So we have to find this value. So how to do that, how to find the singularity value? You have to find the Jacobian, then you have to find the inverse of that one. So once you find the determinant of that one, you are getting L1 L2 sine theta 2. Once you multiply, you find this determinant of this particular part, you'll get that it will be L1 L2 sine theta 2. So in this case, if you see, singularity occurs when this particular value equal to be 0. If this will be 0, means this value will be become 0, and L1 L2 did not become 0. So what happens when theta equal to 0 and theta 1 equal to 0, theta 2 becomes 0. So what happens, if you see, this is my robot arm like this. So in zero condition, this is my L1, this is my L2. So in this particular configuration, it will be going to reach 180 degree, means this angle will be 180 degree or 0 degree, whatever you want to do. Either it can do like this, or it will be reached in this particular, in the back side, if it is completely rotated. In this two condition, here singularity conditions will be coming. Huh? Singularity conditions will be coming. So that's the thing you have to understood clearly. So for each and every configuration of robot, you have to first find the singular point. So always try to avoid this kind of thing. Otherwise, in your motion planning or trajectory planning, you are not able to do. So you will going to lose 1 degree of freedom or some other way. So it will, even though like your joint will be moving, but your end effector velocity will be not moving. Here means like it is a kind of, that thing is called singularity configuration. Huh? So mathematically also you have to explain. If anyone want to ask you something, then you can explain mathematically how this thing is happening. But similarly, if you see, this is the condition for what, maximum velocity is occurring. But in this case, if you imagine, in this particular case, yeah, in this particular case, what is happening, so whenever you need minimum velocity means minimum work will be required, means like minimum work means like minimum energy will be required. Because if you want to do some kind of task in some space, you need minimum energy, so that you'll get benefited from that. Huh? So in that case, this determinant of J should be maximum. This determinant of J should be maximum. If this will be maximum, then your velocity will be minimum. Your velocity will be minimum. Your velocity will be minimum. Huh? Your velocity will be minimum. So what will be the condition? Maximum means this particular value will be your like what, sign of 90. It will be either sign of 90 or 270, or in that way it will be going on. Huh? It will be because maximum at theta 2, maximum at 90 degrees. So here what happens, it will be like you, always you want to work in this particular like 90-degree kind of thing. In this particular workspace, you can able to work. Huh? In this particular workspace, you can able to work. Because if you see, like while you writing also, na, just imagine in your hand, what is happening, it is already energy optimized condition. So if you completely flex your hand, and write in the blackboard, though it will be very very difficult, but after some certain amount of time, you will going to be like difficult. Definitely what will happen, you'll get lot of like you can feel discomfort continuously if you're writing. So what happens, you have to little bit, you have to bend. So while you're writing in your copy and pen also, if you see between the your hand posture, if you check, it is kind of optimal position. Either it will be nearby, it is not exactly 90, but it will be approximately like 70 to like some angle will be there. So that is the optimal conditions. Huh? That is the optimal conditions where you can get less energy, you can use less energy, and you can easily do for longer period of time. But imagine while you're writing, you extend your hand and try to write in your copy for 3 hours. It is not possible at all. You are not able to generate the forces to write also. Huh? You will not able to generate. So that's the condition for this one. Then different like singularity will be there. Boundary singularity means robot reaches the workspace edge. So that is the boundary singularity. Posture singularity means two or more joints align with each other. Elbow will be straight. Then reach singularity means last three axes of a 6 degree of freedom are aligned together. Then what will happen? Reach singularity will be going to come. So this also they used to ask, so types of singularity and other stuff. Then next thing will be why next thing will be, we'll try to cover this motion planning with 5 to 10 minutes what I have left. So in motion planning, if you see, like, motion planning is nothing but, in layman term, if I say what is the motion planning, so what happens, one point means like one thing has to move from point A to point B without like what, create damages to the environment. Means like it has to follow from A to B without any deviation or any obstacle hitting or something. That is coming under the motion planning. How a robot should move from one configuration to another while avoiding obstacle and satisfying all the constraints it will be required. Now, why it is necessary? It will be for collision free path, efficiency in operations, complex environment kind of thing. What is the physical significance? Smooth transitions, prevent sudden stops or jerks, ensuring mechanical reliability, productivity, and different other kind of thing. Same thing again. And what are the components mainly we going to use to do the motion planning? So first thing is already inverse kinematics part. Second thing is your path planning, then trajectory generation, then low level control. These are the four things you have to deal with to do the motion planning properly of any industrial robot. Any industrial robot, for maybe for a mobile robot, this inverse kinematics part will be not there, but you need path planning, trajectory generation, then you have to control that particular thing. Inverse kinematics already we discussed. Then path planning. Path planning is nothing but finding a list of joint positioner poses that move the robot from start to a goal configuration. Constant like collisions or joints limits are typically considered in this case. Then same thing, this path planning, what you have to do, the converting a path into a time based. So in this case, trajectory, to do develop the trajectory, you have to convert to this a time based frame. So path, if I say like path planning means, suppose I am going from point A to point B, I am following one path, so that is my path planning. But if I say I am going to point A to point B in 5 seconds, 5 meter per second I am following. So that time part, if you add, that will be coming under the trajectory generation. Then low level control is nothing but the, once you get all these things, you have to how the robot will be going to move. You have to write some equations and the physical kind of, like, you have to have some control algorithms like PID, like MPC, different algorithm, controller algorithms to follow that particular trajectory. Then trajectory generation, as I told you, it converts the geometric path into a simple time-based profile. So this theta t is nothing but your angular displacement, that position of the actuators. Then theta dot is the velocity of the actuators. Then theta double is the acceleration of this thing. And if you do one more derivation of this particular part, that theta triple dot, that becomes jerk of that particular actuators. So why we need this? We need that particular thing as like for smooth motion. So we need this for smooth motion. So if you see, next thing will be going to draw. Just imagine this is your robot arm. This is your robot arm. This is your robot arm. So this will be like X and Y. This will be my XY, and it is going to another point. This is my final point. This is my start point. This is my goal point. It will be going through intermediate point. It will be going to intermediate point. So this is my, suppose, X1 and Y1. This is my X2 and Y2. This is my X3 and Y3. This is maybe XG and YG. What happens when it is in this position, one theta 1 will be there, one theta 2 will be there. So this particular, if you want to define this in a way, this is called your joint space configuration. So in joint space, I going to define this particular part. I can say theta 1 and theta 2. And task base, if I define this particular robot, it will be called as X and Y. X and Y. Similarly, for joint position 2, this is my second position. So in this case, one joint will be there. So I can say that theta 1, this is my point 1, theta 2, position 1. Here maybe the in this is my joint space, this is my joint space, this is my Cartesian space. This is my Cartesian space, XY and this thing. This is my Cartesian space. Here X1 and Y1 will be there. Similarly, you can write for each and every point. If you can write for each and every point. So if you see now, while it is traveling from this point to this point, final point, it has to follow this theta 1 is, this theta 1 has to follow one, theta 2 has to follow one path. This thing also going to follow one certain path. So what happens, we have to make this particular trajectory very very smooth, so that there will be no jerk to the joints, there will be no jerk to the joints. This is my theta 1, theta 2, this is my theta 1, and there is no jerk to that particular joint. So each joint is nothing but a consist of a motor. So if it is suddenly going to start, then what will happen? Suppose it is start initially it has zero condition, so speed velocity will be zero. Suddenly if you give a like acceleration 10 or 12, so definitely you are going to break that thing, similar to while you start your vehicle. So if you suddenly like accelerate, or maybe you are going in a five gear 5, then if you suddenly reduce the speed, then what will happen? It will be jerk will be going to happen. So in this case also you're going to develop like this. So joint space we already discussed. What is the meaning of joint space? Means this theta 1, theta 2, theta 3. Then Cartesian space means all x, y, z, and this other value, other rotational value, that is called roll, pitch, and yaw. Roll, pitch, and yaw. In x direction, rotation is called roll, y direction pitch, then z direction yaw. Then why you need this one? We need this one for what? Prevent the abrupt movements in the movements part. Then joint limits, actuators limit, all these things we going to develop. Then different methods are there. One is polynomial method, trapezoidal method. Then different like equations will be there, because we have to develop. Huh? So if you going for use for polynomial method, if you see this is my polynomial method of general polynomial equation. This is my position. I can write in this way. If you see here, four variables are there. Huh? Four coefficient a0, a1, a2, and a3. For 3 degree of polynomial, 3 degree of polynomial, we will need four coefficient. We need four coefficient. If I go for 4 degree of polynomial, I need five coefficient. For 6 degree of polynomial, if I go, sorry, 5 degree of polynomial, if I go, I can have six coefficient. So in this case, what will happen? Four boundary condition I have to give, means initial, when the position will be at initial position will be there. Just imagine this is my, this is one trajectory curve, one is this is my t, this is my theta, this is my theta t, and initially it may be started and reach up to this point. So here this may be have some point like this, not this one, this one. So here maybe initial time equal to 0, the here time equal to tf. So initial time some value will be there here, theta 0, and final some theta value will be there, that is theta f. Then in this particular zero condition some velocity will be there, and that velocity, initial velocity will be definitely will be rest condition means 0. So this theta dot will be always, this will be always 0, and final velocity reach that point means it is top condition means this will be also 0. So using this four condition you have to solve this equation, but solve for the coefficient value. So once you get the coefficient value, if again put that and you get the equation, you will get the equation of this one. Once you get the equation, you can easily find the position, velocity will be the one derivative of this one. Then second derivative will be the acceleration. So once you solve this condition, you will get like this. By applying this condition, this will be a 0 and this will be also 0. By satisfying, then if you put here, you will get some this value. If you put that, you will get this kind of. Once you will get this one, and then you can solve for the equation. Once you put this value, you can solve for the equation. Then what happens, you can plot this value at some condition, so you will get the position like this. Position means if you see your degree is varying from what, 10 degree, it will reach up to 30 degree. It is from 10 degree, it reach up to 30 degree. Then as velocity will be there, so this equation you have to derive again. Then you'll get the velocity will be, profile will be like this. Minimum will be 0 at the initial position, and final also you will get the 0 degree per second. Then acceleration also, if you see initially it will be at 0, then it will be reached to this position. If you see in this particular case, what is happening at 0, you are getting some kind of accelerations. You will having some acceleration. That acceleration will be having maybe 100 or 110 or 125 you are getting acceleration. So what happens in this particular case, the demerits of this cubic polynomial is that you will get at 0, means like here velocity will be 0, then suddenly you are getting acceleration at 0 will be around, suppose imagine this value will be how much, around 125 or something, 25 your degree per second. So what happened initially at 0, but you are suddenly giving acceleration as how much, 125 degree per second. But that is not practically feasible, because what happens, your joint will be going to damage suddenly if you give us increase the acceleration, or suddenly you are making like breaking break. So what happens then, your issue will be like your actuators will be going to damage because of vibration and other stuff, huh? That's why we have to make some smooth kind of transition here, some kind of smooth kind of transition here means, or we can directly give this particular velocity acceleration also zero. As if you make the acceleration zero and final acceleration will be zero, then what will happen, then there will be a small, like slowly it can start and reach, so your velocity thing will be very much smooth. So what happens, how are we going to do that? To do that, we have to go for pointic polynomial. This is means fifth order polynomial. So fifth order polynomial, and here condition will be again, extra condition will be coming, the acceleration condition will be coming. So here if you see six coefficient a0 to a5 and six conditions. By using this six condition, you can easily find out the equation. In that condition, this particular value will be zero, this value will be also zero, so that you can get what, you can get smooth acceleration, and their trajectory will be also very smooth. So maybe in this case, they will going to ask you, so why after third and fifth, third order polynomial you took and fifth order, why not fourth order polynomial? So fourth order polynomial, if you take, as I told you here, how many variables you will get, you will get four variables, four boundary five boundary conditions, huh? So five boundary condition means, here position at initial and final, two velocity at initial and final, and one thing you can add for initial acceleration you can add. But if you add initial acceleration means, it is going in a acceleration, and final acceleration you don't have to condition to satisfy. So you are not able to solve, if it means like your final thing will be not zero. So it is starting at zero, but your final condition will be not, it will be having some value, so that you are definitely while it is stopping, then it will be get what, lot of like a jerk, it will be get lot of jerk. So generally we don't use fourth order polynomial to generate the trajectory, huh? Some or that's the reason, this is also important case they used to ask, huh? Then just other methods are there also, like polynomial method for degree 5. If you see here, it is if you see initially at zero, but if you see now it is starting at like this is my acceleration, it is retracted zero, so it is coming at zero. But in the previous case, if you see, it is like this, huh? The curve will be like this, it is starting suddenly. In the previous case, it is starting suddenly at zero only, it is see, when time is zero, it is going up to this value, and when again at the end, it is going to suddenly zero. So that's why this polynomial is not, whenever you need for some like straight line kind of thing and other steps, you need this one, sudden travel and other steps. But the other case, you don't need this one, huh? Then trapezoidal profile is also there. So trapezoidal profile is also there, but this is depend upon the application you can use. You cannot use it generally. So these are the most of the things related to today's session. So, but I a little bit go a little bit fast. So yeah, some of anyone, I stop it here. So anyone having any query, then you can ask me. Yeah,
Okay.
anyone having it.
Yeah, okay. Okay, Dr. Manta. I think thank you for your presentation and thank you for your enrichment session. So any participant, any query is there, please raise your hand. So I think we can able to allow the mic as well as, and if you want to write your query in the chat box, that also you can write in the chat box.
Sir,
Yeah,
I have,
some. Yeah,
sir,
go ahead, go ahead.
yes, I have enabled Dr. Saranges Ripan and Nisha Bhatt. I have allowed to speak. Please unmute yourself or you can ask your question.
Okay, Dr. Sarangi, if you have any query, I think mic is allowed to you. Just unmute yourself and ask your question. Similarly to Nisha Bhatt.
Yeah, Dr. Soraj, I can going. I'll share this slide so you can share with the participants so they can go through that. If anyone having any query, they can message me my WhatsApp number or mail. They can, so maybe we can in touch.
Okay, it's okay, sir.
Okay.
So thank you very much, sir, for your presence and sharing your idea and thoughts. We will see you again in near future.
Thank you, Dr. Suraj, for inviting me, and it's pleasure to talk with the participants. So I hope I actually it is a kind of very fast session. So maybe some people will be having some issues. So anyone having any issue, then just they can free to WhatsApp me in my number. I in the slides I going to provide that.
Sure, sir, sure.
Yeah. Thank you, sir. Thank you for your enlightenment session about the robotic kinetics and the motion planning. And we will definitely see you in the future session also, sir. Thank you. Thank you, sir. Thank you for all
Thank
the participants for joining the session. And we have another session is there at 2:30 p.m. So that session is also enrichment by the faculty who's going to join for